All right, welcome back everybody to video 3. We're going to be talking about groundwater flow. You see the learning targets there. Go ahead and pause the video, take a look at those. Any kind of method that you're using for taking notes, make sure that you have that ready to go, and we'll get started.
All right, so it looks like the first thing we're talking about is hydraulic gradient. Okay, another term I like to think about for gradient is this kind of slope, right?
Mm-hmm.
Okay, so you can talk about the slope of the water underneath the surface.
Yeah. And we did this when we talked about streams and the gradient of the stream, right? So we're talking about how steep or not steep it is, and it's pretty easy to calculate. What do we need to know in order to calculate the hydraulic gradient?
It basically is just kind of like rise over run that I'm sure you've done in math class quite a few times. So we have height 1 or H1 and we have H2, and we can see those two labeled there. We're going to subtract those two numbers to get the overall height, and we're going to divide that by the length or the distance.
So we want to look at the change in elevation of the water table itself, right?
Yeah.
Separating the unsaturated and the saturated zone, that water table,
Yeah.
and over the length of that distance. Okay.
And that can help us try and figure out which way water is going to flow in an area, because we know the water is going to be flowing between those pore spaces.
And I'm thinking that the steeper the hydraulic gradient, the faster the flow is going to be, but there are some things that we're going to have to think about in addition to.
All right, so if we take a look at this map, this actually is a special kind of map, but it's a topographic map. And if you can take a look at these darker black lines there, they've got numbers attached to them, and those show elevation. And there's also blue numbers in there as well that outline the elevation of the water table, all right, underneath the ground. So we can actually calculate the hydraulic gradient of this area because we have a scale down there at the bottom that gives us a distance scale, and then we can calculate the change in elevation of the water table.
So I want to think a little bit about how we would get this data. You could have your phone or your GPS out there, and you could be looking at the elevation of the land as you are walking around on the land. But how do you know the elevation of the water table underneath you?
So that'd be kind of a tougher one. You wouldn't just be able to use your phone for that one.
Right.
So that's where we start using well or log data or well data. So we would start digging holes.
Okay.
Okay, and they would drill a hole down and they would measure and drop something down to see how deep the water table is.
Okay.
So they'd have some sort of sensor on there to be able to determine how far beneath the surface the water table is.
Okay, and another good example here that we're seeing, if you look at the pattern of the blue lines, which are the elevation of the water table, and if you look at the black lines, which are the elevation of the surface, they're mirroring each other again.
Yeah.
So we are here recognizing that the water table and the land surface are pretty much in line with each other. Okay.
Yeah, and to think three-dimensionally too, like the left side of our picture here, that's like the top of a hill almost, and it's going downhill, excuse me, towards the right. Same thing's happening with the water table. So I'm at 1,100 feet on the left, and it's flowing down to the right towards that 700 feet.
And if I was going to put flow directions on here, like we might be doing in class, where we're going to ask you to draw some flow directions as arrows, you're going to make the arrows perpendicular to the elevation of the water table, right? Because water is going to try to go down the steepest way.
Sure.
So you can think about putting your arrows on there showing the flow direction, but you could also think about how you might calculate the hydraulic gradient here. You've got a scale in the bottom right corner, and you have the elevation, so you could measure the distance, and you could divide the change in elevation by that distance.
Okay.
All right, cool. So now we're going to take a look at a little bit more complex view of this, and that's Darcy's Law. What does Darcy's Law help us to do here?
So basically, excuse me, if we look at the flow velocity, it's going to be kind of related to the slope of the water table. So the steeper the slope is going to be the larger pressure difference between 2 points. So I think about like if I had like a tube or like something I could fill with water, and if I held it flat, there's not going to be much pressure going in either direction. But as soon as I start tipping that tube, or like my water bottle here, as soon as I start tipping it, I got more pressure pushing down, so the water is going to come faster out of it.
Okay. And then there are some other things that are going to impact this, though. We have to think about the permeability of the material. So if the material is not very permeable, that's going to restrict the flow. And we also have to think about the viscosity of the solution. We think about water as just being water flowing through, but in fact, that water could have dissolved some minerals, it could have dissolved some soil, and it could carry some of that with it, so the viscosity of that solution could be different and slow it down.
And when you say viscosity, you're talking about how like resistant the fluid is to flow. So I think something with a high viscosity is like syrup, and like water is a low viscosity.
Right.
So water is going to be able to flow faster than a syrup.
So if we try to talk about Darcy's Law and what it really tells us, it helps us get a handle on how fast the water is going to flow based on the slope and the permeability and the viscosity of the fluid.
And
It takes those things into account.
And this is super important if you've got a house that has well water, like my parents have a house that has well water,
Okay.
and one of the summers they pumped too much water out and they actually completely ran their well dry. And they're asking, like, how long is it going to take to recharge? I'm like, well, there's all kinds of factors because you're towards the top of a hill, and it's going to take a while for water to recharge that area. And we had to figure out a lot of different things to help figure out how fast it would fill up again.
Okay, well, that's important to know. All right, so let's go on to the next slide.
All right, so now we're going to start looking at the exchanges between streams and aquifers, and we have a couple different diagrams here. If you take a look at the first diagram, it's a diagram of a gaining stream, and if I think of the term gaining, or the stream is gaining, it's gaining actually water. And if we take a look at the diagram here, if you notice the water table, which is the top of the aquifer, kind of like that dashed black line, it's labeled there, water table, it's actually the same level as the surface of the water that's in the stream. So therefore, the aquifer is feeding that stream, and that stream is gaining from the aquifer below it.
So that could be the source of water in a desert stream, for example, where there's a drought or there isn't a lot of rain, yet you see a stream that's flowing. That water source may be the aquifer underground.
Sure.
Okay? And then the losing stream, in this situation, the stream itself, the level is going to feed the aquifer, right? So the aquifer level is lower, the water table level is lower than the stream level, and water will soak through the stream bed and recharge that aquifer.
Yes, so that's all we got for you guys on this one. So go to your class website, take a quick quiz, and we'll see you guys tomorrow.
Bye, guys.
See you later.